I know that you know how to balance reactions, you've been doing it for a long time, but when we start talking about balancing redox reactions, we have to pay attention to one more thing, because redox reactions involve moving electrons around, so I need to make sure that I'm keeping track of those as well. So you don't really have to write this down, but what I want you to do is I want you to think about how you would have balanced reactions before. You're simply counting atoms, and you would have balanced it like this, and that would have looked great. You would have counted up the hydrogens, the oxygens, the sulfurs, and you would have made sure that left side, right side was correct. But let's pay attention to the electrons. So find the atoms that get oxidized, the atom that gets reduced, and start figuring out electron movement. So it turns out that sulfur here started out as a -2, finished up as a +4. That meant it went up in oxidation number, so loss of electrons, oxidized. Oxygen started out as a 0, neutral, and went to a -2, so that means it's been reduced. If I start looking at the total number of electrons that have been lost, total number of electrons that have been gained, counting up and using those balancing numbers, it turns out that sulfur in total had a movement of 12 electrons, so did oxygen. So not only did my numbers of atoms work out, my number of electrons worked out. If electrons got gained, they came from somewhere. Electrons that got lost had somewhere to go. Electrons are balanced as well. But if I gave you this reaction and asked you to do exactly the same thing, well, let's go through it a little bit quickly. You count up the atoms, you do that. If I started looking at the oxidized and the reduced atoms, chlorine has been reduced, iodine has been oxidized. If you're not really sure where those come from, think back to the previous video about identifying oxidation numbers. If I count up the total electrons lost, total electrons gained, chlorine has had a movement of 12, iodine has only had a movement of 10, so the electrons are not balanced. Now I can't just have electrons being gained out of nothing, and I can't have them disappear into the great void. I have to have the electrons balanced. So even though this reaction looks balanced, it's not balanced. However, there's a couple of things that we ignored altogether. This is the thing that is why we said it's not balanced. And this is the other thing I said about electrons have to be accounted for. They have to have a place to go, and they have to have a place to come from. But the part that we ignored that was just sort of interesting but otherwise useless trivia for you at the top was this idea about acidic solution, but what's actually happening in acidic solution. One thing is water is available, and I could perhaps get water involved as a reactant. Water maybe could gain electrons or lose electrons. It could somehow be involved. And I also have some hydrogen ions, or perhaps you recall hydronium ions. They're floating around and they could be made available. And I ignored all of that. But if I start thinking about these other things that are just sort of in solution, maybe I can find a way to balance this. So we're going to go back and we're going to balance this again. Now, I want to warn you first up that it's going to look like really kind of weird steps or a lot of steps or complicated steps. They're really not. And we're going to try to focus our attention on this. So what we'll do is we'll go through it slow time, and then at the end we'll summarize it, and those will be the steps that we need to take. So we're going to start by separating them into what's called half reactions. And that just means that I'm going to take the chlorine thing with what it becomes after the reaction. And I'm going to do the same thing with the iodine. Now I realize that I've got oxygens unaccounted for, but don't worry about it. We're going to make sure that that works out. The other thing is, what I'm doing here works really well on paper, but of course you can't have an oxidation reaction without a reduction reaction. So I can, on paper, separate them, but I can't chemically separate them. Okay, first thing, we're going to kind of work our way from big to small. The big things, the most obvious things, are like the chlorines and the iodines. So I'm going to balance everything except, or I'm going to balance those. So balance all atoms except hydrogen and oxygen. So starting big, going small. Chlorine is already balanced, one on either side, but the iodine, there's 2 iodines on the reactant side and only 1 so far on the product side. So I'm going to balance it. Starting big, going in 1 step smaller, I'm now going to balance the oxygen. I'm going to do that using water. So where I've got 3 oxygens on the reactant side, I'm going to add 3 water molecules to balance the oxygen. Now I know, but we're going to take care of that in a little bit. With the iodine, same kind of thing, but don't forget I've got 2 in front of the iodate ion, so that means I have to add a total of 6 waters. Okay, moving one circle in smaller, now I'll balance the hydrogen. So counting up hydrogens, but I'm going to balance that using H+. Remember, I had acidic solution, so I had water and I had hydronium, or hydrogen ion. So counting up how many hydrogens need to be balanced, I put that many H+ on the opposite side. Same thing with the iodine. I need a total of 12 hydrogens, so I have 12 H+. Now, I know what you're thinking.
I wonder how many peanuts I can fit in my mouth.
Okay, I did not know you were thinking that. But we're eventually going to, when we put them together, start canceling things out. Don't do it yet. That's like our last step. Okay. Now we ran into a problem last time because we didn't have the electrons balanced. So that's our last step. That's our smallest thing that we need to balance. Here's where things get weird. Electrons are negative, so I have to think about it in terms of adding negatives. Okay, so far on the reactant side I have a -1 and a +6, or 6 pluses. So I've got a total of 5 pluses on the left, and I've got 1 minus on the right. So I'm going to bring the 5 plus all the way down to 1 minus. So I add 6 electrons. Please do not think of it as just balancing off the 6 H pluses, because it's more than that. It's the entire side. On the second half reaction, total neutral on one side and a total of, I've got 2 minuses and 12 pluses, 10 pluses on the product side. I'm going to bring the 10 plus down to neutral. So all I can do is add negative charges. So I'm going to add 10 electrons. Now this is key. You'll notice that I've got one where the electrons are gone on the reactant side and one of the electrons are on the product side. That's important. One of those is a reduction, where it's gaining electrons. The other one has to be an oxidation, where it's losing electrons. So that has to be a thing. You'll notice though they're not balanced. So the next thing I need to do is make sure that all the electrons gained equal all the electrons lost. Total number of electrons have to be the same. So I'm going to do that using probably a trick you learned in grade 9 or grade 10 math. I'm going to multiply one reaction by, in this case, 5, and the other reaction by 3, so that the total number of electrons will be equal. Hopefully you can read the dark purple. It seemed like a good idea at the time. So now I've got 30 electrons on one side, 30 electrons on the other side. I'm finally balanced. But now I've got too much stuff. So what I'm going to do is I'm going to combine and reduce, or reduce and combine. So I'm going to cross things out. Now, the electrons have to completely cancel out. That is the whole point of what we're doing. But the other things, I had 6 H pluses on one side that didn't cancel out, and I had 3 waters on one side that didn't cancel out. That's okay. That'll be part of my net overall reaction. Now I'm going to combine them, and I end up with this final thing as the balanced chemical reaction. Okay, a lot of work, but once we get used to it, we'll be able to go through it quite quickly. So here's the summary. Here's all the steps that we had to do. If you need to pause and write those down, awesome. I'm not going to pause for long because I'm always on the move. I'm going to give you a couple actually that shouldn't have given you the whole thing, but I want you to try and balance that top one, but on your own, working through those steps. And by the time we're done, you should be able to balance redox reactions in acidic solution. Now you might be wondering, probably not, but you might be wondering, how do you balance something in basic solution? We'll take care of that in class. The good news is it's actually very, very similar. The bad news is it's actually very, very similar. And I know that may not make a whole lot of sense right now, but you'll see what I mean later, because in a basic solution, we don't have a lot of H+, but we still go through the process of using it. But we'll deal with that in class. See you then.